So as we move into talking about Henry's law and the dilute solution standard state, we need to think a little bit more about the units of the Henry's law constant in order to be aware of some gotcha caveats that come out as you see different expressions for the Henry's law constant. So here we have the expression that we're using for the fugacity of component I in the liquid phase. Again, this is in the dilute solution standard state, or D triple S. This is telling us that in the limit where xi goes to 0, that this activity coefficient for the dilute solution standard state will go to unity, right? And we know that we have our Henry's law constant here. And if we look at this, right, we know the units of fugacity are equal to units of pressure. And we know that the mole fraction and activity coefficients do not have units. And so therefore the units of the Henry's law constant in this dilute solution standard state formalism are pressure, so that carries through and makes sure that the fugacity has the appropriate units associated with it. So we're going to be using this type of expression as we move throughout the course of talking about absorption and stripping, for example. For vapor-liquid equilibrium, if we have ideal VLE using the dilute solution standard state, then we'd have a situation where we'd have the partial pressure of component I in the vapor phase, or the ideal gas fugacity, right, equal to x sub I times the Henry's constant, right? And so this is just fugacity coefficient in the vapor phase is equal to fugacity coefficient in the liquid phase. Now we're just using the dilute solution standard state. And so what we'll see from this is when we make our XY diagrams for absorption and stripping problems, we're going to have a situation where Y is given as the Henry's constant divided by pressure times x, and this will end up defining our XY diagram equilibrium information for absorption and stripping problems. Now, there are a couple other forms of what end up being called the Henry's law constant that you may see out there. One, your book talks about it as being a case of H for component I prime. This particular form is defined as a ratio of concentrations, right? So if you had a concentration of I in the liquid phase divided by a concentration of I in the vapor phase, this sometimes is defined as a Henry's law constant. It's really a partition coefficient because it gives you a dimensionless read on what the sorption of a vapor is into a liquid, for example. But this particular form is dimensionless. And so as a result, we would use it very differently from how we're going to use our expression for the Henry's law that we'll use along with fugacity. So you may see something like this come up where people are discussing a Henry's law constant that is dimensionless, and that means that it's going to be defined as some ratio of a concentration in the liquid relative to a vapor, or vice versa. Usually it's defined this way because usually the question is, what is the concentration of the solute in the liquid phase? And so then in this case, you could multiply the concentration of the solute in the vapor phase times this version of the Henry's constant to get the concentration in the liquid phase. Somewhat similar to what we're doing in our VLE analysis, but again, there's a difference here in terms of the units that are involved. Alternatively, if you go and look on the NIST chemistry web book, right, there's a whole bunch of data up here. This is an excerpt of one of the tables for, I think in this case, ammonia. And here we're looking at Henry's law data for ammonia in water. And in this particular case, you'll see that NIST gives you a temperature-dependent Henry's constant, and it's given as the equation that's indicated right here. I've written this out in a little bit what I think is a little more readable form over here, but ultimately there are two parameters associated with this particular equation. So we have a prefactor, right, that is given, and then we have this derivative term that enters into an exponential. We'd put in the temperature of the system that we're working with, and we could calculate what the NIST webbook calls a Henry's law constant. The units, you can see, are given by the prefactor in moles per kilogram per bar. And so this suggests a different form ultimately of the equilibrium relationship yet again, right? So this is suggesting that this case of H is being defined as some concentration in the liquid phase divided by the partial pressure of the solute in the vapor phase. Right, and we see that from the units. In this case, the concentration of the solute in the liquid phase is given in moles per kilogram, so molality units here. And so in this case, the numerator would be moles of ammonia per kilogram of water in this case. And then that would be divided by the partial pressure of ammonia and the gas in equilibrium with the water. And that would give you this Henry's law constant as NIST defines it. Likewise, right, we could turn this around and say then that if our goal was to understand what the concentration of I was in the liquid phase, that we could multiply this form of the Henry's constant times the partial pressure in order to get that, and we could make the units work out there. So this is a different form, right? It's actually the inverse of essentially what we're seeing in the expression we're going to be using. So this is important to keep in mind because this is the kind of thing that you have to be careful about when you go and look for data in other sources, and it's particularly, I suppose you could say, problematic in the sense that the chemical engineering and the chemistry ways of doing these things are in some cases different, but certainly as you go into some of the environmental spaces and other things like that, there are different ways that different communities answer this question of how much does a solute partition into a liquid phase from a vapor phase, and often they all sort of call them Henry's law, but we can do a little bit of unit analysis and be a little bit careful about our way of approaching this in order to prevent ourselves from making what could be a catastrophic mistake in terms of doing this analysis.